All right, so everybody looked at the homework that I handed out last time, and it's I want to return to that and spend some time on it because this is the end of the chapter, basically, cross-flow heat exchangers. I hope that everybody was able to do this. Were you able to understand a lot of these? And let's go ahead and, if you have your table, we'll flush it out. And let's go at the top. I know some of it was really basic. I wanted to be very simple when we get started. Any changes? First 5 lines. These look okay? How about the B's? We worked these out last time. The equations for the volumes. What I computed was the fraction of the heat exchanger volume occupied by basically the passageway for fluid 1. I know it's finned, but it's 32.9% and then 65.6%. And there's basically a 1.6% occupied by the plates. So for the fluid occupying this wavy fin for passage 1, 33%, and it's about 67, 66%, about 2% for the plates. All right, how about the frontal? This is where I stopped doing both sides. Who got the area frontal for fluid passage number 2? 0.898, and that's square, foot squared, right? Good. Let's continue on. What about the hydraulic diameter? That was just reading the chart, 0.00696 feet. Thumbs up if you agree. And then 0.01522 foot. Alpha is the area of the heat transfer per unit volume, and it has units of foot squared divided by foot cubed, and I'm going to do this. It was 166.9 for the passage 1, and 157.9, 157.9. Okay, then what's sigma? That's that minimum free flow area to the frontal area, and 0.2904 and 0.6007. Those two numbers, were you able to get the two sigmas? So it's about 30%. You have the frontal area, but then that fluid has to get into the free flow or cross-sectional area to flow, and that's only 30%. So 100% of the area to 30% for fluid passage 1. And then it's 60% for the fluid passage 2. All right. What about that minimum free flow area? This is for the entire heat exchanger, and it's 1.714 or 1.713, and then 0.539. That's foot squared. That's that minimum free flow area. How about the heat exchanger area? It's 695.3 square foot in that volume of that heat exchanger. So that's how much area that you have for heat transfer for the first fluid. And then the area for the second fluid, who got a number? 658, 657.7. Very good. All right. Now, the area thin divided by the total heat transfer area, that's just reading off of the diagram. It was 89.2% and 88.8%, right? Very good. I encourage you just to skip the fins, the fin efficiency. Maybe that was a little short-sighted. I need more space, so I'm going to insert a new page. The length of the fin which is the passageway divided by 2. If I look at it, these fins pretty much are like this. And then they're brazed to this plate and brazed to that plate. And what's happening is this symmetry line, and the spacing is B, between the plates for that fin there, cross-sectional area, that the flow goes through. And so you're thinking about L being the length of each fin. So these are be treated as a fin with adiabatic tip. All right. So we already know for side 1 and in side 2, we already know what B is. So what about the thickness of the fins in foot? The thickness of those fins, reading from the chart or the illustration given, 0.0005 foot, and then 0.00067. Should I go and look where to get those at? They're going to be right in there. The fin thickness, right there on this diagram. And likewise, there's the fin thickness for the other one, the other surface. All right, we have to calculate the m of the fin. The m of the fin is the square root of 2, the convection coefficient for that side. The thermal conductivity of the fin was given to be aluminum, and the thermal conductivity given, and the thickness of that fin, so each side has a different one. Well, let me just say, I'm going to calculate those H's in a minute, but let's go ahead and give you the H and calculate the M, and you can just make a note of this. It's 26.5 and 17.9. This is in units of inverse feet. What we do is we multiply the length of the fin times that M parameter. When we do that, we get it's 0.46 and 0.61. Now we can calculate the efficiency of the fin for each side, which is given by the hyperbolic tangent of ML divided by ML. And so the fin efficiency, there was a few extra steps. I didn't want you to get bogged down in that. 0.936 and 0.891. I said just to round those off to 90%, but there you go. There's more detail there. Now let's jump back. When you do that, the overall fin efficiency, and you have to have those areas, which we already did. The overall fin efficiency comes in a little higher, 0.943, 0.903. Okay, how do we calculate G? We showed it right here, the mass flow rate over the free flow or the minimum flow area. And we calculated 1.167 and 3.707. Thumbs up, you agree? Good? Okay. Now, how do we get that? We got the Reynolds number. This Reynolds number was wrong, isn't it? Yeah, that Reynolds number is wrong. Thank you for verifying that. So it's 4391 or 4,400, somewhere in that vicinity. Very good, thank you. I should give you bonus points for that, huh? Yeah, you put that in your submission of the homework. Say, hey, I found the error that was given in the lecture, so extra points, please. And this, I think, is around 593, 598. It's not going to make much of a difference, because how do you get that Colburn heat transfer factor? You have to go to either two ways. You go to the plot and you say, okay, for this first one, it was around 600. So right there is 600. You come up and you read that factor. True? So you do it graphically off a fairly poor graph. or the textbook curve fit some data. And I found some other data. I didn't bring it, but there's a big fat textbook, handbook of heat transfer, and it actually has these two surfaces in numeric data. So I put those into Excel. So for the first surface, at that around 600 Reynolds number, 0.0161. What did we say it was, about 0.015? And then 0.00308. There's no way you're going to get 3 digits. You can tell I did it in Excel with some data that I got from another source. All right, and then the fanning friction factor, 0.0735 and 0.0089. Now there's two things when you're reproducing the results in the textbook. That's what we're trying to do, verify them and check things out. Right here is probably the biggest difference. So if you said, I think it's 0.015, not 0.016, it may not seem like a big difference, but you can't get 3 significant digit agreement in your final answer with what they have in the book, can you? But if you use exactly the same numbers and the same equations, then you can get 3 and 4 significant digits agreement between what your calculations are and what's in the book. So right there is probably the biggest difficulty in getting a great match. All right, so now we have the J, and we can now calculate that H. That H, what did you guys get? Around 20.2?
I got 18.84,
and 12.3. So, and this is BTU per hour foot degree F. So what did you get near 20?
I got 18.84 and 11.95. Almost.
Yeah, okay.
Maybe we could go through that, because I got really, really low numbers.
You got really, really no numbers?
Yeah.
How about, did you count for the hour and the second difference? Because what are the units on G? Yeah, so 3,600 is needed.
That's right.
Because second and hour, yeah. Probably would have been better just to convert G into mass per hour and use that as your primary unit of time. All right. Yeah, I can show that calculation. I have it in Excel. So let's take a look at Excel. But first of all, the equation is do you have the same J? If you have the different J, you're not going to get the same answer. And then the G should be straightforward. The C sub P is given. And every now and then I'll make a mistake and I won't put over Prandtl number to a coefficient, the right coefficient. I may mess that up. But it's this is just, if you can type it in correctly and not mess it up, given. This is the wild card, that's the uncertain one. And G was given. You just have to use the well, first of all, you have to calculate G. M dot divided by the free flow area. That was right here. Did you get these values for G? And these are pound mass per second foot squared. You got those values of G? Then it's all in the J, the Colburn heat transfer factor. So you must have gotten a little lower than 0.15 or something. Okay. How about the area for the heat transfer? Now that we have the H, we have the area for the heat transfer. You can do it for one passage, multiply by 12 to get the total area for all of the whole heat exchanger. Let me see what I've got here. I don't have a separate line for that where I actually, maybe I do somewhere else. But you go back up here to this, right here I have it. Area heat transfer for the whole heat exchanger. So I really didn't need that. All I have to do is take this line up here and divide by 12 if I really wanted to report it. True?
Yeah, that was 20.
Did that make sense?
That would be 24 because you're looking for atom that one.
Well, you have 12 passages for fluid 1, 12 passages for fluid 2. Yeah. Yes, and then divide it again. That's right. By that. Now I wanted to calculate the resistance thermal, which is, let me jump to another page here so I can explain it. Let me jump actually to a new page. So last time I talked about there's a plate, there is half of our fin surface on one side and half of our fin surface on the other side. And just think about the symmetry and the symmetry. And so what we were interested very much in finding is the overall heat transfer coefficient, U. Okay? There's another way of doing it as well. I really need UA, don't I? Because that's what I'm really needing. And the reciprocal of UA is the overall resistance to heat transfer. And that resistance is in 3 little series. It's come out of the fluid 1, go through the plate, conduction, and then into fluid 2. So the resistance for the getting out of fluid 1 and getting into the solid so it can be conducted through the plate is 1 over HA. What you have is you have the convection coefficient on that one side. Then you have the area heat transfer on the one side. And then because it's a thin surface, you have the efficiency overall for the one side. And we calculated that overall efficiency. Let me just try and highlight some things here. This, change color here. This overall efficiency, 94.3%. That convection coefficient, H1, 20.2 BTUs per hour foot squared. And this, you can do it for 1/24 of the heat exchanger, or actually you could do it for the whole heat exchanger. You just have to be careful. You have to match the correct area for the plate when you want to include the plate. But because the plate's going to have negligible resistance or small, you can neglect it and get away with it. But let's do it with the whole heat exchanger. So the whole heat exchanger has the area for the heat transfer 695.3 foot squared. You come over here, I'll skip the plate for a minute, and we have 1 over the efficiency, overall efficiency for the second surface, convection coefficient on the second surface, area heat transfer for the second surface. Here are the numbers. We found that this one was 658-ish, roughly. The convection coefficient was around 12.3, and the overall efficiency was 90.3%. So you could do it on the 1/24th, or you can do it on the whole thing. All right, now this is the tricky part. If you do it on the 1/24th, how many plates do you have to go through? It's bad. If you don't, you have to do it on the whole heat exchanger. You have the thickness of the plate, the conductivity of the plate, and then the area of the plate. Remember, this is the total area for finning to get out of the fluid 1 to the plate. So it accounts for all of those passages in both sides. So what you're going to have is you're going to have do the area of one plate, and I would multiply by the number of passages and multiply by 2. Make sense? Okay. Well, when I did that, we found that the resistance is 0.1234754. Over here it's 0.000137. Those units are degrees F hour per BTU. And then the resistance for the part in the middle, I have to go and look at the Excel code because I don't really have it in front of me. Well, do you mind if I jump to the Excel? All right. That's for the one side. Okay, resistance. It's 1%. So the resistance is 64%, 63, 64, okay, 35, 64, and 1%. So this was the 64%. That part's just a whopping 1%. What'd I say, 30 what? 35? Does that add up? Yeah, that adds up. 35%. Actually, I think I may have done it on the 1/24th section right here.
That's the total, right?
I did it. I did it like I described last time for one plate, and then 1/24th, 1/24th. So these numbers are a little different than I just gave you, but it's 1 over the effectiveness HA.
So that would be the resistance of only one pass, right?
That's right. It's the resistance. Mm-hmm.
So you want to multiply by 12.
Then, yeah, let me see what I did right here. I reciprocated, then I multiplied by 2, and I get the UA. I think it was a little more logical not doing it for the 1/2 fin surface, one plate, but to do it for all of them, but I don't have that on this sheet here. And I mean, you could put in the thickness, thermal conductivity, and calculate that number. Then sum them up, get the percentages. Now what you have is you have this is R total for the whole thing. If I want UA, I invert 1 over R total. And if you want to check, take this number and add that number, and then reciprocate it with your calculator. Let's go ahead and do that. You have a calculator? Do you see what I'm asking you to do? Take this resistance, add them together, reciprocate, and then give me UA. $4,708. Anybody else? Same. So we verified it, and when I go back to the Excel code, you'll see that the Excel code is really close, 4078. It's a little different. Oh, it is about 1%. Okay, very good. Thank you. So now we have UA. Let's go back. This is our discussion of how to get that UA, just like I showed last time. So hopefully you were able to do it. Now, what about that pressure loss? I suggested that you just neglect anything but the core. True? So just neglect everything but the core. So if you did the pressure loss neglecting the in and out, the acceleration effects, you could get a value that is right at 8.9 and 30, and the units are lbf per foot squared. True? Wasn't this design supposed to give us, what, 8 and 35? So what's the difference? Well, first of all, I was a little wrong on telling you could, as a first approximation, you can cancel the density over the mean density right there. True? That was the mean density. That's true. You can do that, but if you want to get a good agreement with what the textbook has, you have to have the best friction factor. So if you're reading something off the chart, if you don't read it the same, you're going to have a different number. That's probably the biggest source of error. This row right in this equation, which row is that? That's the row inlet 1, isn't it? Yeah. And you could have some errors with the mass densities. All right. Well, if you go to page 234 of the textbook, let me jump to see if I can get that textbook pulled up. There's page 234. All right. There's an itty bitty little typo. Did anybody catch it? You want to, you know where we're hunting in the discussion for the typo, right? It's just what I was just talking about. So maybe you were trying to reproduce the results, right? And I'll grab a copy of this. Last chance to impress me if you found this error. That's exactly it. Did you know it all along? You're just doing a quick comparison. Yeah. So let's see, where was this at? All right. Well, here you can tell from this equation right here, and it's consistent with the textbook, although it's not gotten out of the textbook, that for the core friction term, what are the two ratios? It's the ratio, the density in divided by the density, mean density. It's the in plus the out divided by 2, or you could do the average temperature, average pressure, and calculate a slightly different mean density too. But what did they have? Control V. What did they have there? So if you're trying to compare, and okay, I'm going to modify and I'll use their friction factor and I'll use their value to really double check your equations, you go, oops, that took me a while, like what's going on? How come I can't get better agreement? Now let's jump back and say, let's say I want to calculate the pressure drop neglecting inlet, outlet, and acceleration effects. There's the values. Okay? That's with the correction and not using the typo in the textbook, but using the correct density in the equation. What happens if I want to account for all of them, if I want the pressure loss with all of the effects? Well, it's 9.0 instead of 8.9. It's a little more because the entrance, outlet, and acceleration. And it's 32.3 instead of 30. I want to spend just a little bit on those terms. Let me go to Excel code. Maybe it's readable. So what they do is they break it down into terms. T1, and then T4, T3, T2, and T3. T3 is the dominant one, the core. And you can see that it's 98%, almost all of it. on that side, and it's like 93, 94% on this side. I got a little shifted on my numbers here, sorry. But what is the equation for T1? Let me come back because I can't write on this, but here you can see I have to do something plus 1 minus something squared. That's the alpha squared, but there's a coefficient, k sub c, in that term. So let me do this. Let me go back to Excel. Maybe it's even back to this one. Yep. Here it is. So for the entrance, this is T1. Do you see that? It's so you have 1 plus sigma squared plus kc. What is sigma squared? It's a ratio of the free flow area to the frontal area. So it has to cram into 30% or it has to cram into 60%. That's what sigma is. So either for this problem it was like 0.29 or 0.60. But what is that kc? That was our coefficient for contraction or fitting into the tube. And then likewise over here in the T4 term, you're going to have a KE. That's a exit, expansion. All right. Well, how do you get KC and KE? You would go to an illustration like this, true? But it's not fitting into round holes in a plate blocking it. What is the configuration that we have? We have basically a passageway that's like this, true? And this is some blockage and then another side with the passageway. I don't have a good copy of that one. Here's a good copy of this one. How many people have their textbook? All right. It's on page 159 of the textbook. We have sigma for the fluid in channel 1 is equal to, it's 0.29, let's round it off to 30%. And we're doing that configuration, so that configuration's in the lower left corner of those 4 plots. And you give me your best k sub c for not only that sigma, because that tells you where you're at on the x-axis, right? But you also need to know what the Reynolds number is, and the Reynolds number was around 600. So this is Reynolds number of 600. And I'm going to try and pull it up electronically. Wish me luck. So people that have a textbook have the advantage. I'll try and copy this off. And go to where I can annotate and write on it. So it's not as good an illustration as that one. And we'll put one more page. We'll go like that. And I have to shrink it down just a little bit. All right. So where are we at? We're at 0.3, aren't we? So there's sigma of 0.3. We're looking for the contraction. Which group are the solid lines? Those are the expansion. Which group are the dashed lines? Those are the contraction. True. And it ranges between laminar flow, the curve that's the highest on the case of C, or is that KE, to infinity, that's this curve right here. And here's 2,000 and 3,000, 5,000, 10,000, and then in Reynolds number of infinity. So for Reynolds number of 600, what curve do we go to? Laminar. So we find the intersection of 0.3 for sigma with the laminar curve. What did you read? About 1.15. But if you take a look at what they chose, I'm not picking on them, but I'm trying to help you because you probably struggled with it. What value did they use in the simulation of example 3.5? Did they use 1.15? They used 0.4. So it's a lot different, isn't it? 0.4 is like almost a very high Reynolds number. All right, that's for Kc. Let's do it for Ke. The same side, it's 0.3 for sigma, the fluid one side. And what do you get for Ke? Around 0.25. So we should have used 0.25 and about 1.14, but verify that for me. Can you see where they picked the value of Kc? They picked it to be 0.4, which doesn't make sense on side 1, and 0.47, which doesn't make sense for Ke. And it should use, looks like it's better at 0.25. Okay, now what we do is go to the second fluid side. The second fluid side had a Reynolds number of, what did you say, 4,000? And this side, side 1, had a Reynolds number of 600. We use the same diagram for both sides. Remember, fluids here, fluids there. Both of them have to get into it, and both of them pop out of it. And the book used for the second side 0.28. Okay, it was about 0.6, wasn't it? 0.6. What do you pick up? Should be right in this vicinity, close to 5,000. 3,000 and 5,000. What do you pick up? 0.4. And then the last one, case of E, which the textbook used 0.10, right in here. Read across. 0.08. Make sense? All right. So if you want to verify, you take a look on page, these are on page like 233 of the textbook, and you'll see in the upper part where they have the loss coefficients for entrance and exit, but they really don't match the diagram. For example, 3.5. But guess what? It's pretty small. Most of it's the major loss anyway. But if you go to example problem 3.6 and you look at their K values on page, so this is example 3.5, this is example 3.6. I would take a look at the middle of page 237. They have the same heat exchanger. They just changed L's. The same two components in that compact heat exchanger. And what do they pick up for Kc1? 1.15. What do they pick up for Ke of 1? Well, they pick up 0.27. I would say that's the same value. We're reading a diagram, right? And what do they pick up for Kc on 2? 0.40, same value. And what about the Ke, the same value? So, hey, it's a book. Somebody wrote it. They're not perfect. But when you're trying to compare and reproduce, it can be very frustrating. All right, so now that you have this problem set up in Excel, did we finish all of our analysis? Did I answer all those questions? I think so. Oh, you know what? I typed out a bunch of these. You could read them if you want. Maybe I'll scroll through them and show you. Some of those coefficients for T1, T2 do end up being negative, which is a little difficult for me to to handle because I want to sum them up and then get a fraction. You know, what's responsible for that loss, but with that negative sign. I think these are all correct in this vicinity. Yeah, I believe they're all correct. Yeah, and there's that error I mentioned. What was the error? Rho sub m. All right. I think I need to stop this and go back to Excel. The last thing that I wanted to do is I wanted to say, let's run now example, because this is a running code. I know it's too long to fit in one Excel spreadsheet. You had a question?
Yeah, can you explain again what you were thinking about dividing the...
Yeah, okay, let me try it a number of different ways. I'm trying to figure out how to do that. So I know that to me, I like to think of one plate, and I have half of a fin side and half of a fin side right here. And so I can get U. U is an overall heat transfer coefficient. And maybe I'll put area of one plate, and I'll put one over here, and I'll put the one over the resistance on the one side for 1/2 plus the full resistance going through. This is R for 1/2 on side 1. And then we have resistance of 1 full plate, and then resistance of 1/2 of side 2. It's kind of getting out of the fluid and into the finned side 2. All right. Now, if I said that I want to multiply by the total number of plates in the box, that would be 2 times the number of what do you call those? Passages. 2 times the number of passages. So, the area then of one plate multiplied by the number of plates would give me the total area of all plates. I'm not doing a very good job of processing this in a way that I can explain it. Maybe I do this. This was the thickness of one plate, which is the same as the thickness of all the plates. The conductivity, which is the same. And this was the area of one plate. True? So focusing on that term, if I put 1 over the number of plates in the box, in the whole heat exchanger, I'd have 1 over the number of plates. And now it's like thickness divided by K times the area of all the plates. So either I focus on the blue equation, which is the 1/24th section, or I do that. Let me do this. I have 1 over the overall effectiveness for that side times the convection coefficient for that side times the area for that side, which was 1/2 of the area of a passageway. But when I come over and I multiply by 1 over the number of plates, the number of plates is 2 times the number of passages. So I'm not doing a very good job here. I need to skip it down there. 1 over the effectiveness. I have the convection coefficient. I have 1/2 the area of one passage times 2 times the total number of passages. So I have the area of one passage times the number of passages. These go away, and I'm left with 1 over H times the area of that whole heat exchange in the whole heat exchanger for side 1. I'm trying my hardest, but I don't know how to do it better.
That makes sense.
Okay? And then the same thing here. All right. There was one last thing I was going to show you. What was I going to show you?
Excel file.
Okay, the Excel file. And that's right. For the new problem, example 3.6, they said change your dimensions. Make it a little longer and changing your dimension. Let me see. What dimension did they give us for example 3.6? All right, they wanted this to be 1 foot for length 1. They wanted length 2 to be 4.5 feet. And they still wanted 12 passages. And the length 3 is approximately 1.3 foot, but there's a little inconsistency. It's like, hold it. Either your end plates have a different thickness than the plates that are in the middle, or something. Okay. But there you go. That's the 1.3, which is close enough to 1.274. And now with that, what we can do is you have the same mass flow rate, and a lot of these calculations now have been updated in Excel. Did I change KC and KE? I can't remember which one I'm using. These are the better values, so let me just copy and paste them right there and get rid of it. And copy and paste. All right. So our G's change. Why do our mass velocities change? Because they have different areas to go through. Let me do this. I don't think the sigmas change. No, the sigmas stay about the same. All right? They are the same, actually. They're not changed. And let's see, the H's, there's a 20.5, and now it's about 8.72. Why is that one so much lower? It's a different speed, isn't it? We used to be going at a Reynolds number of 4,000 something. Now we're down to 3,100 for that side. It's slower flow. This one is slightly higher speed flow. It's 600 instead of 611 instead of 598. So you get all the values are updated for the convection coefficients. Okay, your friction factors have to be updated. Notice that I made a little routine to call that. If you want, I'll show that to you very quickly. Go to developer. Hold it. Maybe I can't do that. Escape. Then the Visual Basic. And so I just made some routines like this. So the friction factor for that one. And basically I put if things are in a log-log scale and then did a little interpolation in between points on a log-log scale. So that's the Excel code to make that happen. And this data, I didn't read off of it. That data I got out of a different source. I found it for both the friction factor and the Colburn heat transfer factor for both of those surfaces. Probably. So those get updated, and then we could take a look at our T's and we get our pressure losses. Now you can see what happened to the pressure loss. Went up. And what about the pressure loss over here? Down quite a bit. So you change your dimensions, that's changing the length of the passages, and then it changes. Okay, this problem, actually we're going to revisit, not after chapter 3 is all done, but we revisit it in near the very end of the semester in chapter 6. All right. So thank you very much for your attention. I'm sorry, but it's computational. A lot of this is just brutal computational work. Thank you.